Hello everyone, welcome back to my channel. Today we will solve some problems from the topics that we have discussed in my last lecture. So I recommend you to take pen and paper and solve all the problems along with me. Before going into any problem, try to solve the problem by yourself and then go to my video for any clarification. If you find any mistake, please let me know in the comment box. Thank you. Hello, here you have December 2016 UGC CSI net question. We have to solve a commutation relation that involves the position operator plus derivative operator, comma, cosine of position operator. Okay, let's solve this. To solve this commutation relation, we need to know the following two properties of commutation relation. The first one is linearity property. What linearity property says? Suppose in the commutation relation, in place of one operator, if you have addition of two or more operator like this, then you can break down this commutation relation into an addition of two different commutation relation that involves a comma c plus b comma c. Okay, in place of first operator, if you have addition of three operator, then there will be three such commutation relation has to be added. And the second such property you need is, suppose if you have an operator and then function of some other operator, then this can be simplified. The derivative of the function with respect to that operator, second operator, and then the commutation of first operator and then second operator. This you need. Okay, here you can see in the given commutation relation, in place of first operator we have addition of two operator, and then in place of second operator you have function of position operator, cosine of x. Okay, so for that can be simplified using second property. Okay, so let's do that. So this commutation relation has to be acted upon by some well-behaved wave function, and assuming that that is psi. Psi is my well-behaved wave function. Let's use the first property, linearity property, and break down this as a commutation relation of two commutation relation. So x comma cosine of x of psi plus d by dx of cosine of x psi. Okay, next, so using the second property, one can write this commutation relation in the following way. So derivative of cosine of x d by dx of cos x, d by dx of cos x, then commutation of x comma x. So we know, okay, let's come to that later. And how this can be written here. Okay, let's use the commutation. What is the commutation of a comma b? AB minus BA. Here we have d by dx of, cos x psi plus, no, cos, not plus, minus cos x d by dx times psi. Okay, so we know these two operator commute each other. X will commute with x, so this becomes 0 plus. So what is, so here you can use chain rule by using cosine of x as constant term, differentiate first d psi by psi with respect to x, cosine x, you have cosine x here, plus keep psi as constant and differentiate cosine of x. It is minus sin x minus sin x, and then here you have cosine of x into d psi by dx. So here you can see these two can be cancelled. Minus cos x time d psi by dx plus cos x time d psi by dx, and we have minus sin x times psi. So now you can remove this psi. Your answer is minus sin of x. This is your answer. Here you have June 2013 UGC CSIR net question. So the problem is, given the commutation relation between A and B, which is equal to the identity operator, which of the following option is correct? So if you see all four options, it is asked to find basically the commutation relation between e raised to a comma b. A and b are operator. Okay, so as we have discussed earlier, that whenever you have an operator and functions of some other operator in the commutation relation, you can simplify using the following formula. Take the derivative of the function with respect to the corresponding operator, and then again take the commutation relation between the operator involved. Okay, now the given commutation relation e raised to a comma b can be solved using the above property of commutation relation. So what is, so our function is e raised to a. Take the derivative of e raised to a with respect to a, d by dA e raised to a into the commutation relation between a comma b. Okay. Now what is the derivative of e raised to a with respect to a? Which is e raised to a, and the commutation relation between a and b is given here in the question itself, which is identity operator, which can be written as identity operator, and any term which is multiplied with identity operator is the term itself. Here we have e raised to a operator. So the answer for the given question is e raised to a. So only option A is matching. So our answer is A. Here you have net December 2014 question. Given the commutation relation between position and momentum is I in the unit of h-cut, then you have to solve the commutation relation of x comma p times e raised to minus p. Okay, so using the same property that we have discussed earlier, that if in the commutation relation, if you have an operator and functions of some other operator, then this can be simplified as derivative of the function with respect to the corresponding operator, and then the multiplied by commutation relation between A and B. Okay, now the given commutation relation is x comma p times e raised to minus p. Okay, use the same property. So here our function is p into e raised to minus p. The derivative of the function with respect to p, here we have p e raised to minus p times x comma p. So what is the derivative of this function with respect to p? You can use the chain rule. Del p over del p, it will be 1 only, and e raised to minus p plus um, p times derivative of del by del p e raised to minus p, and then whole thing has to be multiplied with x comma p. So this is 1, we have e raised to minus p, and this here we have the derivative of e raised to minus p with respect to is minus 1, so we have p times e raised to minus p times what is the commutation relation between x comma p, that is given as I here in the question itself. Use that. Here you have I, so if you take e raised to minus p commonly out, here you have 1 minus p times e raised to minus p multiplied by I. So your answer is this. This is your answer. Here you go, June 2016 UGC CSA net question. We have to simplify the commutation relation that involves Lx, Lx, Ly, Lz, where Lx, Ly, Lz are orbital angular momentum quantum number. Let's solve this. To solve this problem, one needs to know the following properties of commutation relation. The first one is distributivity property. Distributivity property. So in the commutation relation, suppose if you have an operator and then product of two or more operator, then this can be written as a comma b, commutation relation of a comma b, and then c, and multiply the commutation relation by b, that between a and c. Okay, this is one. Also this is same thing you have to apply when you have a product of two operator at first and then the third operator. If you have the same thing, you can write here a multiplied with bc, a comma c multiplied with b. Okay, the next property that you should know is the commutation relation that involves the angular momentum quantum number, operator. Suppose you have the operator for angular momentum components of Lx, Ly, Lz, and if they appear cyclically in the commutation relation Lx, Ly, then this is equal to IH cut time Lz, and if it appears Ly, the commutation relation between Ly and Lz is IH time H cut time Lx, and Lz commutation relation between Lz and Lx is equal to IH cut time Lz. If there is any IH cut time Ly, if there is any change in this operator, then there will be a minus sign. Okay, so using this property, one can write the given, at first using the distributivity property, one can write the given commutation relation in the following way. The given commutation relation is, so for sake of easiness of writing, I am going to omit the cap which denotes the operator. So I have Lx, Lx, Ly, Lz, which I will be writing at first as Lx times Ly, Lz plus Lx comma Ly. This is using distributivity property, as you can see here, and commutator with commute with itself. So here commutator Lx comma Lx. So this operator, same operator, it commutes, it gives 0. So this term is going to 0. I am going to omit from now. So it Lx comma Ly and Lz can be written as Lx Lx into Ly Lx comma Lz plus Lx comma Ly Lz. So you can see now you can use the commutation relation between the orbital angular momentum operator. Here Lx Lz is coming. So what you can do, this can be written as minus of Lx Ly Lz comma Lx plus, so what is the commutation relation of Lx Ly? It is I h cut time Lz into Lz. So now you can, so what is the commutation relation between Lz Lx? This term will be I h cut time Ly. So put it there, minus Lx Ly I h cut time Ly plus I h cut Lx Ly Lz. So here you can take it out, I h cut time Lx you can take it commonly out. So plus I am taking it out, I h cut time Lx. So if you take I h cut time Lx, you have Lz squared. Okay, and here I h cut time Lx, if you take, you have minus Ly squared. That's all. This is your answer. So the given commutation relation is equal to I h cut time Lx cap Lz cap squared minus Ly cap squared. This is your answer. Here you go, June 2017 UGC CSI net question. Two vectors are given in matrix representation, and if they are orthonormal to each other, then what should be the value of A, B and C? You have to find the values of A, B and C. Okay, so let's solve this. So let's take the first vector. First vector is phi1, get phi1 A0, and second vector is get phi2 BC. Okay, the condition is given as orthonormal, means if these two vectors are orthonormal, what should be the value of ABC? Let's use the orthonormality condition of these two vectors. If they are orthonormal, the inner product of phi1 with phi1 should give us 1, and then inner product of phi2 with phi2 should give 1, and the inner product of phi1 with phi2 should give 0. So basically we are using the orthonormality condition between two vector. Inner product of phi I with phi j is equal to delta ij. Okay, now let's use this property and then find the values of ABC. Okay, so given phi1, what is the bra phi1? It's a column matrix. So bra phi1, let's find the bra phi1 is equal to A star 0, and then bra phi2 is equal to B star C star. Okay, so let's at first, using this property, we'll find the value of A. Inner product of phi1 should give us 1, and that is A star 0. A0 should give A star A plus 0, which should be equal to 1. So mod A squared, basically mod A squared should be equal to 1. So A should be plus or minus 1. This should be the value of A. Now using the orthonormality condition of second vector phi2 let's find the B and C, values of B and C. So what is bra phi 2, which is B star C star times the column matrix of BC. So this should be equal to 1. B star B plus C star C equal to 1 mod B square mod C square. So the summation of mod B squared and mod C squared should be equal to 1. So again we will also apply the inner product of phi 1 with phi 2, that should be equal to 0. Okay, so if you apply this condition, you get A star 0 BC, that should be equal to 0. So A star B plus 0 should be equal to 0, which means the product of A star into B should be equal to 0, but we already found the value of A, which should be equal to plus or minus 1. So the only possibility is B itself is 0. Okay, so this is true whenever you have B is equal to 0. So we found A is equal to plus or minus 1 and B is equal to 0. If B is 0 here, if B is 0, so mod C squared is equal to 1. Therefore C is equal to plus or minus 1. So these are the three values of these three constants A, B and C. A is equal to plus or minus 1 and B is equal to 0 and C is equal to plus or minus 1. Here you have a December 2018 NET question. You have to find the commutation relation A comma X, where A is LYPZ, LZPY, where LZ and LY are orbital angular momentum operator and PZ, PY are linear momentum operator. So let's first, using linearity property, expand the given commutation relation. First, A is equal to LY PZ minus LZ PY comma X, which can be written as, using linearity property, Ly Pz comma X minus Lz Py comma X. Okay, so before solving this, we need to know the orbital angular momentum, components of our orbital angular momentum Ly and Lz, that can be found using this. So we know orbital angular momentum is r times linear momentum, so which is the determinant of this matrix I, J, K, X, Y, Z, Px, Py, Pz. Okay, now what is the components? For that you have to multiply I times Y Pz minus Z times Py minus J into X Pz minus Z Px plus K into X Py minus Y Px. Okay, L is equal to, so this is your x component of orbital angular momentum, y component of orbital angular momentum, z component. Let's write it. This is your Lx, Ly, Lz. So we need Ly and Lz. Let's write that. What is your Ly? Ly is equal to, include this minus, if you include this minus here, you get Z times Px minus x time pz, and Lz will be xpy minus ypx. So we need the commutation relation of first we will find this. Okay, commutation relation of Ly pz comma x. What is Ly? So you can see here Ly involves, okay, we can apply first the distributivity relation and then we can do. So take it this Ly here, let's take it out, the Ly here pz comma x plus Ly comma x time pz. So what is the commutation of pz and x? This will be 0. This will, they commute each other. Okay, this will be 0 plus we need to know Ly comma x. What is Ly? Ly is z time px minus x pz time pz. Here no comma, sorry, here it will be, so here it will be minus x time pz comma x time pz. So here this involves, since this involves x, they to commute each other and then corresponding term will vanish. We need to account only this zx comma x pz. So this again can be written as z time px comma x into pz plus z time x comma px into pz. So what is the commutation relation of this? Minus I h cut times z time pz plus they two commute each other and that will be 0. So your answer is minus I h cut time z pz. Okay, for this. So again we have this commutation relation Lz py comma x. Lz py comma x which will be, using distributive property, one can write this as Lz time py comma x plus Lz time x comma py, and what is no, these two will commute, so this will be 0. So we need have Lz comma x. What is Lz? xpy minus ypx. xpy minus, so we will apply the distributive linearity property and separate it out. xpy comma x minus ypx comma x times py. Okay, here you can see this can be again written xpx. These two, since this term contains x, they to commute each other, and we have only here this xpx, this term here. So this can be written as minus y time px comma x time py minus y comma x y p y. So they two commute each other and its value is 0. Its value is 0. This is 0 and you have I h cut time minus I h cut time minus this minus will be plus. So you have here you have only what I h cut time y p y, and this will be added with this I h cut time y p y. So your final answer is, if you take I h cut time commonly out, you have what zpy. Zp, if you take, so yp, sorry, ypy z zpy zpz. This is the answer. Here you have GATE 2011 question. You have to solve the commutation relation of Lx, Ly, Lz, where Lx, Ly, Lz are orbital angular momentum quantum number. Let's solve this. We know the distributivity property of commutation relation. When you have multiplication of two operator like this in the commutation relation, you can write it as AC times B plus A times BC. So here, applying this to the given commutation relation, one will get Lx, Lz time Ly plus Lx time Ly, Lz. So what is the commutation of this? So what is the commutation relation that involves orbital angular momentum? Here you can write this as minus of Lz time Lx time Ly plus Ly Lz. We know the commutation of Ly Lz is I h cut time Lx. So this, what is the commutation relation of this? This will be I h cut time Ly. So this answer is minus I h cut times Ly squared plus I h cut time Lx squared. So the answer is I h cut times Lx squared minus Ly squared. So that's all. Here you have GATE 2015 question. We need to solve the commutation relation of Lx, Py, where Lx is the x component of orbital angular momentum operator and Py is y component of linear angular momentum. So to solve this, we need to know the distributivity property of commutation relation. Also, we need to know the orbital angular momentum components in terms of linear momentum and position coordinate. Okay, let's first find the orbital angular momentum component in terms of linear coordinates x comma px. Okay, we know orbital angular momentum is r cross p, which can be written as the determinant of the matrix of I j k x y z px py pz. So what is x component is I times y pz minus z py plus j time minus j time, okay, minus I am including here itself, which will be xpz minus zpx plus k times xpy minus ypx. Okay, this is your Lx, Ly, Lz. Let's see, in the given commutation relation, we should know only Lx. So we'll take the Lx from here. Taking Lx comma py. Okay, py lx is ypz minus zpy, sorry, py comma py. Okay, use now the linearity property of commutation relation. If we use ypz comma py minus zpy comma py, here one thing you can notice that this py is coming here also and here also, so they two commute each other. So using distributivity property one can write again this, but both of them will, okay, let's do that. This can be written as, using distributive property y time py pz, okay, y time pz py minus z comma py, minus or minus will appear again, so this is z time py comma py. Here you can see they two commute each other. I forgot to multiply this z comma py, again one more py will be there here. These two will commute each other, so this become 0, and again same operator commute with itself, again this becomes 0, so we need only this two term remains, and again here also they two commute each other. These two are momentum coordinate, operator, they two commute each other, and here you have I h cut, ypy is I h cut, so your result is I h cut time pz, I h cut time pz. This is your answer. Here is the GATE 2016 question. You have to find the Hermitian operator among the four given operators. So, as we have discussed in my previous lecture, when an operator will be Hermitian. An operator will be Hermitian if it is equal to its Hermitian adjoint. How to take for a continuous operator, how to take a Hermitian operator? With respect to a state vector, psi and phi, if these two are equal, then this operator is Hermitian operator. Okay, such kind of operator will have real eigenvalue when they act on the state vectors in the Hilbert space. Okay, so how to find the Hermitian adjoint of an operator with respect to state psi and phi is equivalent to changing ket by bra and bra by ket and take the whole complex conjugate. This is equal to this. Okay, now what we'll do, we'll take the first operator and check the hermiticity. Okay, so first operator is d by dx. This hermiticity you can easily check in other way also. Suppose you are operating the operator once with bra vector, so d by dx, and act one with ket vector, once with ket vector. If both are equal, then this operator is Hermitian operator. Okay, now let's check d by dx operator is Hermitian or not. So I am taking a state vector, well behaved state vector from the Hilbert space and checking this. I am going to take this. this is equal to minus infinity to plus infinity psi star d by dx of psi into dx, which so this can be solved using integration by parts. I am going to take my u as psi star and du is equal to d psi star by dx times dx, and then dv is equal to d by dx psi of dx. Upon integration we will get psi. Okay, now using integration by parts, one can write this as uv. What is uv? Psi star psi minus infinity plus integration v du. My v is this and du is d psi star time into dx. Okay, so it's a well behaved function. Its mod psi squared is nothing but the probability, and this would vanish when the limit tends to infinity. This becomes 0 minus. So you can see here this psi star, since d by dx is can see here. Now I am going to associate this d by dx operator with the whole complex conjugate. This operator is a real operator. It doesn't involve any I. So I can associate with psi star in the following way: d by dx times psi the whole complex conjugate. So your answer won't change. This is equal to the previous integration. Here this term is equivalent to this. Okay, so this is equal to, so you see this is d by dx psi the whole complex conjugate time psi time dx, which is equal to acting the derivative operator in the Bros space. So d by dx time psi star into psi. Okay, so on the left hand side you have psi time. So there is a minus sign which is very important here. Psi times d by dx of psi is equal to minus of d by dx psi star psi. Okay, so since there is a minus sign, it is not Hermitian operator. Instead it is anti-Hermitian operator. Anti-Hermitian operator. Hermitian operator. And so you can also generalize. So all the operator that we are using in quantum mechanics is a Hermitian operator. We know the momentum operator is equal to minus I h cut time d by dx. Since d by dx is not a Hermitian operator, to make it Hermitian we have added this I. Okay, so this combination I time d by dx would be a Hermitian operator, but d by dx is anti-Hermitian operator. D by dx is anti-Hermitian, whereas I time d by dx is Hermitian operator. And if you see kinetic energy, so when we measure the kinetic energy of a quantum mechanical system, we should get a real quantity. So the operator that corresponds to the kinetic energy is minus h cut squared by 2m times d squared by dx squared. It involves second derivative. Okay, so this operator must be Hermitian operator, so that it will give the real eigen kinetic energy as eigenvalue, real value. Okay, so in the 4 option this is anti-Hermitian, whereas this would be Hermitian operator, this would be Hermitian operator, and I times d by dx will be again anti-Hermitian operator. Anti-Hermitian operator, and you can see here this can be written as d by dx time d by d squared by dx squared. Okay, it's a product of two operator. When the product of two operator will be Hermitian, whenever individually they are Hermitian operator and they should commute with each other. Okay, these two operator may commute with each other, but they are individually not a Hermitian operator. This is not Hermitian operator, whereas this is Hermitian operator. So the product must be anti-Hermitian operator. So anti-Hermitian, Hermitian, anti-Hermitian, again anti-Hermitian, anti-Hermitian. So the only Hermitian operator among these four is d squared by dx squared. Here you have GATE 2016 question. It is asked to find the value of the commutation relation of x squared comma p squared. So here we have to use the distributivity property of commutation relation of this kind. Whenever we have a product of two operator in the commutation, you can write this as a times c b plus a times bc. Okay, using this distributivity property, I am going to write the given operator as x squared comma p squared as x time p squared time x plus x time x p squared. Okay, again I already told that whenever a function involves in commutation relation, we can simplify that using the following way. The derivative of the function with respect to the operator into commutation of a comma b. You can use this. So use that here. Use this property here. P squared is a function. It's a function of p. Okay. We can use that. So this becomes, for this term I'll use what is apply this here. So differentiation of p squared with respect to p times x comma p times x. Again x time the differentiation of p squared with respect to p times p squared, okay, times commutation of x comma p. Okay, what this will give? So we have here 2p, and we know the commutation relation between x and p is I h cut, and x time here we have p commutation relation I h cut. So I h cut is a constant, so 2p, sorry, so 2p here. I h cut time is a constant. It will commute with any operator. Take it out commonly. 2 times I h cut. Here we have px and here we have xp. So this is the answer for the given commutation relation of this. If you find this video as useful, please share it to your friends and subscribe for more videos in future.